All right, so for our 2 o'clock panel, the topic is model use cases and requirements, and I will hand it over to Callie Constant.
Thank you. I'm Callie Constant. I work at Johns Hopkins University Applied Physics Lab, and I'm under contract with the PEO Spectrum, doing very interesting and enjoyable spectrum management work. And we have a distinguished panel here that I will introduce briefly. We have Niti Tandon. She's the technical fellow and distinguished member of the AT&T technical staff. Chris Anderson, who turned out to be able to volunteer to join us at the last minute. So he probably came from a much more formal engagement of some sort. and appreciate you being here. He is an NTIA ITS fellow, and many of you probably know him well. And we have Andy Clegg, who is with Google, and we have what I think is a nice, diverse panel of commercial interests as well as perhaps government and DoD interests that in this sharing environment that we talk about, for instance, in mid-band, that should be an interesting discussion, right? So what I'd like to do is I'm going to give a little overview, and I'm going to actually read it because I want to make sure I get it right. And then we will start putting the panelists on the spot by asking questions or asking them to express their opinions about a few things. So, but the overview and the scope of what we're going to try to do here is that since this year's theme for ISART is characterizing and predicting RF propagation and emphasizing clutter, we have to recognize that the methods we apply to accomplish this characterization and prediction are dependent on the mode, the math, the models, and the measurements. Those are the ways we have to kind of isolate how we would attack this. So by way of an analogy, and analogies can be abused, I'll try not to do that, but when we travel, we must choose a mode. We can get on an airplane, we can go in the car, we can ride a horse, and then we have to also, depending on that mode of transportation, choose the path to the destination, and we encounter obstacles in our travels. And similarly, the electromagnetic waves that we launch in doing our business also involve a choice of modes to travel to the destinations, but the modes include diffraction, free space, line of sight, so on and so forth, ducting. We've heard about all of those, and of course, clutter effects. But unlike our travel metaphor or analogy, whatever you want to call it, once launched and once turned loose, they choose their own paths and simultaneously involve all possible modes. Doesn't seem obvious because sometimes there's a dominant mode that kind of overshadows all the others, but they are simultaneously always there. So, and then in those modes, they encounter obstacles, and in this case, what we're interested in, the obstacles that are called clutter. So each mode is typically then characterized with its own math models and measurements that are unique to that obstacle's journey through that electromagnetic environment. So what this has to do with use cases is this. Obviously, the obstacles and modes that are dominant depend on the use case. And thus the math models and measurements we also apply depend on the use case. That's why we're interested in use cases, stating the obvious. And if a use case is important to a particular community of interest, those that are represented here in this panel, that will help define which modes, math, models, and measurements should be the focus of attention to deal with that. So what we're going to do in this panel is we're going to focus on a particular form of physical obstacles, that's clutter. We're going to emphasize the mid-band frequency range in particular, just because that's kind of the most immediate interest these days in the sharing environment. And we're going to identify use cases that are important to us, and then look at the kinds of issues and capabilities which correspond to and are indicated by addressing those use cases. So at this point, what we'll do is ask each of the panelists to take a few minutes or maybe a little longer to talk about why they're interested in clutter and why they want to get engaged in either using clutter and then how they want to use it, and describe what their most important use cases are in terms of limit 3 per customer, all right? So, but what are your most important use cases? And then after each one of the panelists will do that, we're going to ask some canned questions that should be interesting. So I will start with Andy, if I could. You're up at that.
Okay, cool. Let's see. I did have 3 slides to put up at some point, so we could put those up soon. But so let me there. Perfect. Okay, so let me start out. What use case do I represent? What midband use case do I represent? I represent the CBRS world. That's what I've been working on at Google for the last few years. Actually, too many years. It's finally launched, very successful, helping to put AT&T out of business, all sorts of other things, so it's good. I also object to the password for the Wi-Fi, by the way. But in any event, we knew early on in the CBRS realm that clutter was really quite important. If you think about cluttering, we've sort of talked around it a little bit today, but it does one of 2 things. If you don't treat it correctly, you're either going to cause interference or you're going to leave spectrum on the table that you could be consuming, because we're now all sharing spectrum and we all have to get along. And if you're too conservative, you're leaving spectrum on the table. If you're not conservative enough, you're causing interference. But we knew early on that the models that were going into CBRS were much too conservative. We did some propagation testing around the Northern Virginia area in the CBRS band before CBRS was standardized, before we'd adopted all of the models and things like that. And we compared it to, sort of the standard model that everybody tosses about, the basic transmission loss model of ITM. And specifically, we compared it to ITM, 50% reliability, 50% confidence. We took all of our measurements, which was about 2 million different data points, and we compared to what ITM would have told us the propagation loss was. And what we found was, over all of our measurements, all 2 million of our measurements taken over about a year, that what we actually observed was about 30 dB for the mean anyway, was about 30 dB more loss than what ITM would have predicted on its own. ITM doesn't know anything about clutter, it just uses terrain. Amazingly enough, that's very close to the asymptote of P2108, which is 30.8 dB. So, a reasonable match to what P2108 tells you. So we knew right away that the models that we were adopting in CBRS, based upon our collaboration with NTIA and DoD and whatever and others, was too conservative. But we also understand this was a unique situation. Nobody had really shared spectrum with DoD radars in that particular band or in that particular way. So we knew going into it we needed to be a little bit more conservative. But what we found, based upon our propagation loss, that about 87% of the time, the actual propagation loss was more than what ITM predicted. Only about 13% was less. But even that is a conservative estimate for 2 reasons. One is, again, we were using the 50% reliability mode for ITM, when in fact, when we adopted the operational constraints on CBRS, we went with effectively a 95% reliability statistic. So if I had compared our measurements to the 95% reliability statistic, it would have been even more skewed. The difference between what we measured and what ITM predicted would have been even greater. And finally, we looked at it based upon, when you're in the clutter and when you're out of the clutter. And obviously what we're seeing is that in the clutter provides a considerably greater amount of differential between what we saw in our propagation measurements and what ITM would have predicted. So these 3 slides only to show that, yes, clutter matters, and we have the data to prove it. And the initial models that we started out with in CBRS were too conservative. That's also been proven because we have never had a reported case of interference from CBRS into the incumbents, which is federal radars, DoD radars. In the 4 years we've been operating, we have not had a single complaint of interference. That tells us that our models are too conservative. It tells us that we've left spectrum on the table and that we're not using the band as efficiently as we could. The good thing is, tune in next Thursday, June 18th. We have a CBRS 2.0 event at New Americas Foundation in Washington, D.C. There are advertisements about there. We have been working with DoD, NTIA, FCC, and others, and we are finally switching to a mode where we will incorporate some consideration for clutter in the CBRS propagation models. We'll also be making other improvements, and it will have a dramatic impact on the amount of spectrum use that CBRS will be able to support without possible interruption due to incumbent activity. So anyway, the point being here, clutter, this is not an academic exercise. Despite all the matrices you saw in the last presentation, I'm not going to present anything like that. Clutter is real. Clutter has real impacts. And it's a great, the topic of ISART this year is really very topical and something very important for us to take up.
So, thank you, Andy. I have, I guess, a comment and a question follow-up on that. One is, the observation is maybe the reason there's no reported interference is because that stuff we just saw before is working so darn well.
Could be.
So,
well, these are 60-year-old radars we're working with. So,
well, never mind.
Yeah,
okay.
That's very, very old radars.
Okay. But the question I have is one you and I briefly discussed before, and that is, is there a way to divine from these graphics that you're showing right here, what part of that is contributed by clutter or other effects that, in every measurement,
Right.
system and,
Yes.
and has some
Yes.
variability, right? So, and one of the things that struck me when I saw this was how wide it is,
Yep.
and of course how skewed it is, which
Yep.
is your
Yep,
point.
my
but,
point.
but it's wide too, so.
Yeah, great question. So I do not represent that every delta here is due only to clutter. And in fact, we took some measurements. About 90% of our measurements were mobile, but we did take about 10% of the measurements. The car was parked, and we just did static propagation measurements between 2 static points. And even in the static measurements, we saw a considerable offset from what ITM predicted, and we saw considerable variability, short-term, kind of fast variability that you typically see in propagation measurements. And it's due, we could tell it was due to the motion of traffic. Our measurement area was not too far from National Airport, so we would occasionally see significant reflections from planes going into National Airport. We apparently discovered the concept of radar. That was pretty cool. But we saw it, so we know that some of these impacts are due to dynamics in the environment. But the fact that, like a plot that we're showing now that shows a comparison when you're typically above the local clutter compared to when you're below the local clutter, and a significant difference in the offset, 13 dB mean offset compared to 36 dB, I think is a pretty good pointer to a lot, if not most or all, most of this effect being due to static clutter and not to other impacts. But again, it's all wrapped up. Billy's talk earlier today, it shows you how complicated all of this gets very quickly, and it's a point I'll make later. But one of the important things that should come out of this conference is how accurate is good enough. Because if we demand that we need to be able to predict propagation loss, including clutter, to, X dB, what value of X is good enough for what we want to do? And I think it's impossible that X will ever be 1 dB or 2 dB. But if X is 10 dB, is that close enough? What do we consider a good spread for characterizing clutter and its impact on propagation loss?
Thank you. Nikki, you want to go up next?
Sure. So one thing I'll agree with Andy, 30 dB.
Oh,
So 30 dB, I'm not here to talk about ambit because ambit is a conversation that we are having with AT&T and DoD directly. But 30 dB is the number that even when we look through our models, calibrated models versus the models that are used by DoD, 30 dB is the number that comes to mind. So, but anyway, so starting my talk is, Kelly, you mentioned the 3Ms. And what does the 3Ms mean? The 3Ms mean is that there is so much of variability into this particular process. And as AT&T, we deal with this variability all the time. I mean, we rely upon propagation models because we have invested in spectrum, billions and billions of dollars. And it is our DNA to use the spectrum in the most efficient manner. We need to get every bit out of every hertz. And and the first line of defense, or the first step in the best practices, is to use propagation models. And AT&T invests a lot of time, a lot of money, and a lot of resources into propagation models. So we can get there. I'm not saying you need to get there by every dB or every 2 dB, but we can get there by 5 to 10 dB. And that's what we do. That's what we do for our living. And we have our use cases are customer driven. We prepare coverage maps, where our systems are going to be. We don't just work with one band. We don't just work with the mid band. We work with low band and high band as well as mid band. So our propagation models, our clutter models have to be tuned to the frequency. And also we are nationwide. We're not talking about urban, suburban, dense urban, but what we have clutter classes. And actually, Julius gave me a term here that I want to use. We have different RF propagation morphology per area, per frequency defined. And these clutter classes that we define is that a dozen of them, like 30 clutter classes in each of the different categories, right? So we do take the propagation and the clutter as much as to the science as we can. And also you rely upon the geodata, right? I mean, the geodata meaning is the terrain data, and it is the morphology and the clutter data that comes with it. And there is an optimal point, right? Do you need 1 meter resolution? That makes it too much. Or do you want to start with a 30-meter resolution? What we found is the optimum is between 5-meter to 10-meter resolution. And that's what we work with. And that becomes very important because if you're working with these models, especially with these ray tracing models, if you miss a peak, miss a diffraction peak because you have your bin, which is a 30-meter bin, it gets important to have the right clutter data and so on. So our use cases, I'm not talking about ambit here, that you and I will solve on our own, right? Fingers crossed. The use cases that we have is we have a compliance to the FCC. We have to show our license protect to the FCC for every band, every license band that we buy. We have our build-out requirements. We also have to show to the FCC our broadband maps, uplink and downlink data throughputs. And also we have to do coordination. We have to do coordination with our neighbors, Verizon, T-Mobile on the other side, and also with international coordinations we have to do with Canada and Mexico. And these are bound by a treaty, right? So propagation model, clutter modeling, it can be done. We do it all the time. For us, it is a continuous process. It's not a one-time process. We are continuously updating our models. And there is a huge part of it is, we collect derived data. We use the best geo data that's possible or that's available. And we also do a refresh. We do a refresh every 5 or 6 years. So the bottom line is it can be done. You can make the interference and coordination a more manageable problem. And but it's very time intensive and resource intensive and so on.
I do have a follow-up question. Yeah. Am I still working? Yes. Yeah. Okay. You mentioned that you have your own models that include clutter. I guess you import clutter measurements and use clutter. And do you primarily use those to engineer the wireless network itself, manage interference internal to the wireless network, or address the interference in the sharing scenario where the DoD, for instance, or someone else is involved, or all of the above? And if it's all of the above, do you use the same clutter modeling for all of those?
So most of our work is done for our own internal interference and coordination with IMT type systems, right? With neighbors and so on. So our clutter model and our measurement process, right? We do a lot of CW drive tests and do measurements. They are they're more focused on from the base station to the UE, which the UE is on the ground. But so that measurement data or the clutter data is more focused for our use case, but you can take it, I mean, not exactly the way it is, but you can take a lot of elements from our model, from our calibrated model, and we can apply it to radar locations and radar heights and so on. But you'll have to append it with a little bit more different measurement data and so on.
Sure,
So,
the
but
geometry is a little different.
geometry is very, very different,
Yeah.
right? So you do have to
A
make
lot
some
different,
modification
yes.
and
Right.
changes to
Right.
it.
Okay. Thank you. Chris, you ready?
Me. Yes, I should have some slides.
Yes.
And apologies for the eye chart here. I put something together really quick on Friday when they asked me if I could fill in for a couple of other panelists. So I did my best here. This is going to be a fun discussion because I think I may offer some both complementary and contrarian points to what you two are saying. So this could be fun. So Callie, this panel is about modeling scenarios, I guess, applications. What are the requirements?
Yeah.
And so conveniently enough, for those of you that don't know me, I spent 16 years as a faculty member at the United States Naval Academy, helping the Navy deal with some of the propagation problems that they have. And so I've got some background in the scenarios and requirements and the things that they care about. And I'm also part of the IEEE P1944 Channel Models for Mobile Wireless Systems working group, and actually brought one of the scenarios that we're talking about, which is a high mobility scenario. So it gets into some things that you two were mentioning. But so one of the things that I wanted to start off with was when we're talking about these scenarios, whether it's cluttering, whether it's propagation modeling in general, what are the questions that we want to start off by asking? As good researchers, we always want to start with some questions. And it kind of comes to, what information do we have? So what do we know about the environment, the scenario? What waveform are we dealing with? To what level of fidelity and what scale? And one of the things that's interesting, you were talking about using higher fidelity data. One of the things that we observed in the Navy was that higher resolution does not necessarily mean a better prediction. And in fact, if you move from 30 meter to 10 meter to 1 meter, you can actually start getting worse. And when we looked into it, we found out it's because when you get to some of those really fine resolutions, those 1 meter, sub 1 meter terrain resolutions, for example, you might have a little rock on the ground that your propagation model catches just because it happens to land right in the ray path. And it says, oh, this is a knife edge diffraction. I'm going to add X dB extra attenuation for this knife edge diffraction. But it's not a knife edge diffraction, it's a rock, right? And so that's a problem when you get to these higher resolution data sets, is the models don't necessarily ingest them and handle them in an appropriate way.
It's a little non-intuitive, but it's starting to make sense.
It's a little non-intuitive. You have to, right? Are we trying to do a one-time prediction? Or are we trying to do real-time predictions? How often do things change? And it gets to the slow scale and the fast scale, right? We know that our environments are dynamic. How much of that dynamicism do we want to include? We know that environments are not static. We know that construction, if you drove in from the Denver airport, you probably saw that they're building houses like crazy out there. If you used the 2010 land cover database or 2010 terrain maps, it's going to show that as flat ground. But it's not flat ground. It's going to be a bunch of houses here pretty soon, right? So how do those data sets change over time? And what's the cadence for updating them? One thing that I've been harping on for a long time, Callie will probably remember this, right? The world is 3D, right? What are all of the propagation models that I've ever seen that we deal with, whether it's Navy models, DoD models, ITM, what are they? They're 2D vertical plane models, right? The world is 3 dimensions. We know multipath exists, right? We know that mountains exist. We know that out of plane scattering happens. So how do we advance our understanding of not only the baseline model, but we know that clutter in 3 dimensions matters. Which side of the building you're on and how you interact with the building matters. Putting on the Navy hat for a moment. What about weather and atmospherics, right? So this is something that's really important to the scenario, right? I mean, it's not clutter proper per se, but it is something that comes into play. And, you know, again, mobility, how site-specific do we want to get to our description, right? So right now, if you look at some of the classic models out there, what do they have? Urban, suburban, rural. There's some others that have a few. I heard 30. Why 30? Why are we even limiting ourselves to a human countable number of clutter categories, right? We have pretty advanced computer systems now that can handle 15,000 clutter categories.
I think Billy would agree with you on this issue. So.
Yeah. And then, you know, to my final point again, how do we balance deterministic and statistical descriptions, right? And so again, with my Navy hat, what does the Navy care about? The Navy says, I've got an asset that's going to be located in this location. I want to know what happens next Tuesday at 2 p.m., right? I don't want to know on an average Tuesday what's going on. I want to know specifically next Tuesday at 2 p.m. what is happening. So, so this is the scenario. This is my promised scenario that or one of them that we're working on in this high mobility group. And the things that I wanted to point out here, right, are the environment is very complex, particularly when you get into an urban environment. So to some of the measurements that you made, what have you got going on? You've got a transmitter and receiver, and what's the story of how the wave transits between the transmitter and receiver? So we've got diffraction that happens over buildings, or it could happen over terrain. We've got scattering, we've got reflections, we've got diffuse energy. The environment itself is not static, right? There's cars that are moving. Our receiver, in this case, we were concerned about an air-to-ground model. So a receiver is a drone that's moving around the environment. So we've got mobility in the environment. We've got Doppler shifts. We've got, again, it comes back to what's your orientation relative to the building, and how is that going to change the reflection, the scattering, or the losses, right? That all contribute to the PDF that Andy showed. And so, again, getting into the scenarios, this is what we came up with as a group, is what are the key things that we care about in this scenario? And really on the model side, right, it's path loss, it's the Doppler shift, but right in the middle, right, is the clutter and the multipath. And we put those together because we believe that those are interrelated. If everything was line of sight propagation, life would be easy, right? But it's the multipath that cause us a lot of issues. Obviously, we're talking about mobility, link geometry, frequency-specific descriptions of clutter, right? Different materials behave differently at different frequencies. And then, of course, what scale? I like coming back to scale, right? Are we talking tens of meters? Are we talking a handful of kilometers? Or are we talking about interfering with Navy radars 100 kilometers away? Right? So what's the scale that we have to work with? And then what are the degrees of freedom? Like what in the environment or the model may need to change in order to accommodate everything that we're trying to capture in the scenario? Well, I'll save the bonus slide for later.
Okay.
There's a bonus slide. I'll save the bonus slide for later and stop there.
Let me ask a question.
Sure.
I wondered about, because when I saw your slides, I started thinking, you're talking about multipath, and we also hear a lot about delay spread and phase dispersion, and how that affects certainly the desired signal for 5G or whatever, and it's a very important factor in some of the models. So what I started puzzling about is, yeah, I can understand why that would matter for the desired signal. You got to have phase integrity and so on and so forth, right? Does it matter for the interfering signal, the phase dispersion? Is it that important? Should we worry about it?
So you're going to put me up on a soapbox. How can I answer this without getting on my soapbox? This has been something that I've been talking to people about for a long time. The way that we do interference, and particularly aggregate interference right now, is we assume that superposition holds. And what I mean by that is we assume that the signals are linear and the environment is linear, and we assume that the signals are statistically independent. And what that means is at the receiver side, the power of the sum is the sum of the powers, and we can treat everything as an independent path. We run an independent prediction for each path. We add it all up at the end. That said, we know that there are effects in the channel that are not linear. We know, for example, troposcatter can be a nonlinear phenomenon. More power in does not equal more power out necessarily, for example. And so this is kind of my soapbox. And when you say, does it matter? In my opinion, there's a bit of an open question there because of the way that we've chosen to handle the aggregation. We've made an assumption that things are linear and statistically independent.
Yeah.
And are they?
White noise assumption.
And white noise assumption.
Right.
Is it really?
Yeah.
Is that really the appropriate approach?
I was expecting you to say no, it doesn't matter, but you didn't say that. So
I didn't
that's
say
good.
that. Yeah.
So, that's interesting. Okay. All right. Are there any questions from the audience? Can we do that now?
Yeah,
Sure. Before we start launching questions at them?
Yes. So, comment about your question. Phase matters from a signal to noise ratio perspective, clearly, right?
What does the phase
This-
dispersion and
Because you're looking to protect a system, and the system is operating at a certain signal to noise ratio, and the signal deteriorates, and obviously signal to noise ratio goes down. So perhaps from that perspective, it makes a difference, but I don't know otherwise.
I think the jury, I've been exposed to a discussion about that topic, and I think there's some people who make a really good case for, in most interfering signal cases, modeling as white noise, maybe limited clipped white noise is a good way to approach it. But I've also heard some fairly convincing arguments that the phase behavior and the spikiness that you might get out of positive reconstruction or phase reconstruction and whatnot could also make the results of your analysis very different. And I, quite frankly, don't know. So.
Next question. Can we go back to Andy's slides? Andy, I've seen you present the slide a couple different times, and when we get back to it, it's a histogram slide with the that's the one. Right?
Yep.
So I'm a tails kind of guy when it comes to clutter distribution. Tails always dominate the aggregate interference calculation, and so when I look at something where I see I've got some measurements to show me that my no clutter model is potentially in some cases under predicting interference by 50 dB. It strikes fear in my heart. And I'm wondering, it may be that I'm misinterpreting this data, because I look at that, it's like, well, that's sort of a definition of a clutter distribution right there from the measurements that you took. And if I've got just one emitter that has a 50 dB enhancement, right, that's equivalent to 100,000 other emitters that have no clutter, right? And 100 million emitters that if I give them that 30 dB clutter that we were talking about earlier. So I've got just one out there that represents 100 million others. And quite frankly, as some guy who's trying to make sure that we get the clutter right, and so while we still protect the incumbent operations or whatever it is, that scares the heck out of me. I'm just curious what you.
Yeah, I mean, it's a valid point, because when you're adding up powers in logarithmic units like this, the outliers are the ones that dominate. It's a legitimate point. The only thing I would add, Tony, and it doesn't address your question directly. Well, first of all, this is from 2 million data points. So the number of times we were exceeding prediction by 50 dB, that was, very, very limited. But I agree, there may be some cases over very short times where that might happen. But the other thing I wanted to point out about this, and I forgot, but you brought it up, the upper tail is suffering from a little bit of measurement bias. It was mentioned earlier today, measurement bias creeps into the impact of clutter quite a bit. And it's because when you're doing propagation measurement, it's actually hard to get a high dynamic range measurement. You can get, once you get a really good, we had pretty good receiver set up. We had preamps and, good sensitivity, filters and all this other stuff. And we were running decent power on the transmitter. But in the end, we were only sensitive to up to a little over 190 dB of total propagation loss. Once it went beyond that, it was below the noise level of our receiving system. And so these measurements that we present here, these distributions we present here are sort of artificially cut off at the top end because things that were seriously impacted by clutter, we wouldn't have seen in a lot of cases because it exceeded the total 190 dB of propagation loss. But your point is perfectly valid. There are going to be exceedingly rare, if you look at the y-axis, I don't have right glasses on, but the fraction of time that we were under, that we're looking at 50 dB types of, it was extremely small. So I would think in the real world it happens, and I don't think we really should base spectrum policy on that 0.00 whatever percent of the time of occurrences. But your point is totally valid. That would be a serious interference case right there for that 0.00 whatever percent of time that we were exceeding 50% of prediction.
Yeah. Well, could I actually make a small, I guess not a counterpoint, but maybe a thought.
Okay.
If I were an aggregate interference modeler,
yes,
I'm less concerned. There's a threshold, right? So looking at from my perspective, the right-hand side of that graph, the 50 dB extra attenuation.
Yep.
There's a threshold for which you're in a don't care world, right? If I've got 50 dB, 60 dB, 70 dB extra attenuation, I'm kind of in that signal is so heavily attenuated at that point that unless I'm a radio astronomy observatory, I'm not going to see it. From an interference modeler perspective, the left-hand tail is, as Tony pointed out, that's the scary tail. That's that I see 50 dB signal enhancement. Hey, I see 10 dB signal enhancement. That's what's going to dominate the aggregate interference. And again, I wouldn't purport to say what is the cutoff on the right-hand side of the tail beyond which it's a don't care. But I would submit that there is a number that we could say if it's more than X, and we're talking interference, right, that we're in a don't care world. Now, if we're talking coverage, it's the reverse. Yeah. For coverage, folks like AT&T, her use case is different. She cares very much about that right-hand side because that's customers she can't serve.
And let me just make an additional point, and it's to Tony's point. So if you look at the bottom, it was only 3.5% of the time that we exceeded the predicted interference level. And again, this is a 50% reliability, not a 95% reliability that we're typically using in CBRS interference protection. And we don't have the whole we don't have the entire right-hand side of the distribution there because of the measurement bias. So that 3.5% is an absolute upper bound on the number of percentage of time we're exceeding our predicted interference. And I only note this because the improvements that you're going to hear about next week to CBRS with regard to the use of clutter are only going to be applied initially in cases where the device is below 6 meters above ground level, because we want to be fairly certain that the device really is in the clutter layer. And for exactly sort of the point you make, Tony. So totally valid point, but I argue that you don't want to make spectrum policy based upon the very low percentage case, but point very well taken.
Okay.
So we have two hands up. You're the moderator. Do you want to take more questions now?
Yes. Last two.
Okay. Andy, this is great work. You presented this earlier, and I think some of the questions brought up here relate more and more to aggregate interference. And I know Needy, you, I, and Chris, it sounds like also have been that's been in the back of our minds. So if I take this graph and I have UEs and stations, it doesn't take very much, or would you agree with this statement? It wouldn't take very much to get pronounced aggregate interference effects, even using the data that you're showing here. That is 5 or 10 contributors to the aggregate interference, and then I'm in a not such a good place. Is that true?
So maybe. I think two things. One is the proof is in our experience. We've been operating for 4 years, not a single reported case of interference to the DoD. And I think one thing to consider here, because of our sensitivity of only 190 dB of total propagation loss, these measurements necessarily were taken in a relatively confined area. I think, typically extent of 10 kilometers or so in the confined area. Almost all in CBRS, almost all of the DoD systems we need to protect are more than 10 kilometers away, and typically much more than 10 kilometers away. So whatever's going on here, multipath scattering off of a building across the street or whatever, you're not going to see out in the open ocean where an aircraft carrier is. So I would maintain that some of these enhancements that may look like they would add considerably to aggregate interference are due to sort of very localized effects that a carrier out in the open ocean isn't going to see, because they're not surrounded by buildings and multipath and all this other stuff coming right at them. And in fact, it's another point I was going to make, and I'll make it now because we're talking about it, but a lot of the area that is impacted by CBRS, what we call the dynamic protection area neighborhoods, a lot of those, the size of those neighborhoods, which can be 400 plus kilometers in size away from the coast, potentially claim to impact a carrier that could be 200 kilometers off the coast. So we're talking about 650 kilometer interference distance from a 50-watt device, which most engineers would consider that's crazy. But the reason those neighborhood distances are so large is troposcatter, which is, talking about soapboxes. It's been one of our soapboxes for a while. And I know that Billy's working on a lot of troposcatter measurements, and he's going to come next year and prove me wrong. But at least right now, I'm still right because he doesn't have the data yet. But, the troposcatter, I think, is, I've said this before, it's based. Aggregate interference, right? No. So, one thing there's
jump in just one second?
Yeah.
I think you might need ducting.
No. I mean troposcatter.
No, it's
So-
both.
So
It's
okay, but hold on. Yeah,
both exist.
well, hold
exist.
on. So
One's a
I was going
bigger
to say
player than
there's a lot of confusion between troposcatter and ducting. They're two different things. Troposcatter is due to turbulence in the atmosphere at various heights, typically kilometers off the ground, and it causes index of refraction irregularities in the atmosphere. And so it acts as a natural scattering medium for radio waves. And it's virtually always there because the atmosphere is always turbulent. There's always stuff going on. So troposcatter is a persistent propagation mode. It has variations, has diurnal variations and things like that, but it's generally a persistent propagation mode. Anomalous propagation like ducting, where you get sudden index of refraction discontinuities in the atmosphere due to weird atmospheric effects, temperature inversions and things like that. Those are anomalous. They occur unpredictably, and they're usually very limited. They come in like they come in like an explosion. You have this great propagation path for a little bit over only a very limited particular path, and then they disappear as fast as they came in. We do not consider ducting in any of the work we do in CBRS. That's not part of the predictions in any of the CBRS. Troposcatter is more persistent. My point about troposcatter and clutter, though, is that, besides the fact that troposcatter models that are in ITM were based upon data that were acquired in the 1950s and 60s, and ITM itself was developed in the 1960s, closer in time to Marconi than the present day, that there's never been like this complete validation of the troposcatter prediction, which is what Billy's doing now, and he'll prove me wrong next year. But the point is the impact of clutter on troposcatter has not really been very well taken up. Let's say you're a little transmitter, little device in the middle of a cluttered city. In the current model, ITM just assumes there's nothing in its path. It goes out to the scattering volume and comes back down, and that's what adds to aggregate interference. But if there's a little bit of clutter in front of you, your path to the point in the atmosphere that's doing the scattering, suddenly your angle has to be higher up in order to get over that building, which means that the scattering angle in the atmosphere to make that wave come back down to the carrier 200 kilometers off the coast has to now be greater. And the loss from that scattering angle is a very strong function of the angle. I forget the exact power, but it's a very strong function. So if you have to take a steeper path up to the atmosphere, the scattering angle is higher and the loss is going to be much bigger. That's not taken into account in any of the ITM models. So clutter, we'd be curious to see what impact that has on troposcatter. And troposcatter is a dominant thing that determines these big
So
DPA neighborhoods.
Clutter could affect the launching angle of
Correct.
the wave. That's
Correct.
your point.
Correct.
Okay, that's an interesting point.
Yep.
I'd like to move on.
Sure.
One
Yeah,
more
yeah.
question.
Didn't mean to dominate. Actually, I
But that
did mean
was
to
good.
dominate, but that's okay.
Oh, darn.
Yeah.
I can't get my counterpoint.
Oh, you can't?
No, that's okay.
I'm sorry.
Let's-
I lost
okay, it's
control.
okay.
I had to do the
You got-
ducting
go
thing,
ahead.
right? So, okay.
Go ahead.
Thank you. I hope my question will not be as controversial. Going back to the question in Chris's comments on possible impact of aggregate interference from multipath. So in fact, 5G and LTE systems are OFDM based by design, especially made to withstand multipath, okay, and be very robust, okay. The symbol duration is quite long. That manages intersymbol interference, so they are quite robust to that kind of effects. However, other systems, narrowband systems especially, they will not be. They will be differently impacted. So from that perspective, do we need to take that into account when you do the channel models or the per path loss models, especially in sharing studies? Should we calculate not just the path loss impacts, but the delay spread of the channel? Is that the consideration we should be mindful of? Thank you.
So if I think I understand your question correctly, what you're saying is that the waveform that the victim receiver is using matters. And I would agree with that. What I would say though is, in my mind, that would fall under the interference protection criteria for the victim receiver. So if we have a victim receiver that is very robust to interference, then perhaps we could operate more aggressively on the allowed power level, or we could operate with more aggressive settings in the channel model or the clutter model, what have you. Whereas if you have a system that is a narrowband system or a radar system that is much more, what's the opposite of resilient? Sorry, sensitive, thank you, to interference, that again, that interference protection criteria is going to be much more robust, and therefore we may have to be more conservative on the clutter model, the propagation model, etc.
Yeah, good point. Like the modulation, what is it, the level of modulation when you use like QAM and whatnot in the resource blocks, where it is matters, how sensitive it is.
Exactly.
Yeah.
In that line of discussion, the same line of discussion. So I think if you look at, for example, if you look at the paths discussion that we had, the first round of paths we had, like one of the areas that we were looking was the receiver interference management. So what an OFDM receiver does with the multipath is one type of interference management, because we are having multiple received signals coming from multiple paths, and how an OFDM receiver tries to put them together using cyclic prefix and all of those things. That's one type of solution. And I think I agree with Chris that if for example, the receivers assume the dominant signal is 5G, the receivers can be redesigned to address that. And I think that's part of the overall interference management we can assume for the receivers. I agree with that, Chris.
And I would say there are a lot of people at the conference down the street that shall go unmentioned that believe that future spectrum and future spectrum allocations are not going to be clean. You are not going to be allocated an exclusive license and guaranteed an interference-free spectrum. You are going to be required to operate with some level of interference tolerance. Now, I have to put on my disclaimer hat here because I know I work for the regulator these days, and that is not an opinion, may or may of the regulator. It is an opinion of a lot of folks out there in the academic and in the research world that they believe that is how we're going to address this coming spectrum crunch.
Okay. All right, we're going to move on because I have a question. I wrote this down and I'm going to use it, by golly. So, but this question is liable to stir up something even more lively than we just saw. So, give you fair warning. You can take a break, escape, or you can stay and watch. But we'll see. Let me put my glasses on. I want to make sure I read this one right. So, I want to bring this back to the question of clutter and what is bringing us, how do we get to the consensus of how we want to treat clutter and the use cases that are most important to decide how we reach that consensus. So the question is, what are the non-technical issues and concerns with seeking consensus on use cases? Which ones are most important to us, in other words? What are the non-technical issues? Things like, regulatory issues or opinions, belief systems, whatever. Nisi, would you like to take that one on?
Sure. We've been working on spectrum sharing, since PCS, with microwave clearing and then AWS. And let me tell you, technology is never the reason not to share. Technology is never a hindrance. And what I have found is working through PCS and AWS and different stakeholders, right, in TV broadcasters and satellite industry and so on, there has to be an incentive for both the parties to work together. We solve interference problems all the time. We solve it with Verizon, we solve it with T-Mobile, and that is because there is an incentive for both the parties to come to the table and to come to an agreement. And that's what is needed, right? Then, if there is a reason why you need to make spectrum sharing work, the one way would be is to have an incentive on both the ends to make it work. And I think that's the non-technical and the most important issue here right now on spectrum sharing.
Do you have a sense that the discussion of clutter, how to treat it, where to apply models and how to apply models is one of those things that there's disagreement because of what you just described?
So like what I said, right? We spend a lot of time and resources and whether it's the clutter model or whether it is the propagation model or whether it is in the resolution of the data. And I agree with you, it's not just the resolution of the data that matters, whether it's 5 meter bin or a 1 meter bin, but the content of that bin is important too. Like, what is the height of that bin? What is the morphology of that bin? So it's not just the resolution, but also the content of the bin. So we have an incentive to invest in that, right? And there has to be an equal incentive on the other side too, to make this kind of a continuous change and make that kind of an investment. And we're talking about just not time, and it's also a lot of money. And we do a data refresh all the time because new foliage, new buildings, and new structures come up. So there has to be an incentive for both the parties to take that kind of an investment in clutter and propagation models.
Well said. Chris, you want to take that one on? Do you
Yeah,
remember the
I-
question? Want me to read it
the
again?
non-technical factors, and I can bring up two. It's trust and economics, and I'll come back to trust. Right? It's so something that I've learned through many years in working with radio astronomers through spectrum sharing and spectrum coexistence between active and passive systems.
They're the worst.
They're the worst.
They're the worst.
There are. I wish that
They trust aliens.
Well, I wish that I had this slide that I saw from a radio astronomer that radio astronomy observatories are 1 quintillion times more sensitive than a cell phone receiver. And but the issue when I say trust, right? There have been multiple instances. Andy has probably heard of many of these where a system will come in and say, we promise you'll be fine. We promise you won't be interfered with. We promise that we'll stay out of your band, out of your way, whatever. And they've been burned over and over and over again. And so there's an inherent mistrust. And I see the same sort of thing when I see, talking CBRS, right? The Navy has a bit of an allergic reaction to, oh, you're going to come in and use our system. We don't trust you. And so a lot of it is, what are the baby steps that can be done along the way to demonstrate trust? When Andy says, we are not going to interfere with you, what are the things that he needs to do? What are the things that Google needs to do to convince the Navy that they can be trusted? And it also comes to economics. What is the economic or perhaps non-economic incentive for somebody to actually sit down at the table and say, we agree that this is the appropriate model to use. We agree that these are the appropriate data sets to use. Can we get everybody working from the same sheet of music?
That's very well articulated.
Chris, what about if there is a feedback function? In a live network like CBRS or even, let's say, any other mid-band spectrum, if there is a mechanism where you do your own measurements and your own KPIs or whatever metrics you do, and you provide a live feedback to the new entrant.
I've actually seen some interesting research discussing essentially that is, could you, this is a colleague of mine and a friend of mine, is basically, could you watermark every transmission so that if an interference report comes in, you can trace it, you have traceability back to the transmitter from which it originated and be able to say, could you fix that transmitter? That one's the problem. It's not some turn off the entire network in 400 kilometers because we got one interference report. It's this one transmitter that landed in that magical minus 50 dB, the signal enhancement side that's causing the problem, and everybody else is okay. And I think that's a valid, potentially a valid avenue to explore.
Andy?
Yeah, so you took one of my points.
My
Very good. Needy took one. But so I'd say the trust issue, I phrased it a little more cynically. We have to stop making worst case assumptions about every step of the way in order to create the rules under which spectrum is going to be shared. We just have to stop assuming the worst, and we have to take a rational statistical approach to make it more reasonable. And I think that's essentially trust. Another non-technical thing, and we've encountered this a little bit because we've looked at using clutter in CBRS. It's actually a problem getting the suitable open source clutter databases that we could all agree to use. Like right now, there's tons of open source sources of terrain data and very good data. But as far as clutter data, there's not a whole lot of open source avenues for getting really, really good clutter data, unless AT&T wants to give us the 5 meter
But
data.
that's to the UE, it's not to you, right?
Well, okay, that's true. Yeah.
What would you do with it?
And the third point, which is not exactly non-technical, but was what Needy already said, and that is, building a feedback loop so that, the incumbent can let us know when interference is being caused. And in fact, in one of the Paths 1 meeting, I suggested in 3.1, take a different tact. Start with liberal assumptions that will almost certainly cause interference, and then deploy in limited areas, and then find out how much that interference is, and then dial back down from 11 until the interference goes away. Then that way you know you're at the right point of assumptions, that you're not leaving spectrum on the table. We start like we did in CBRS with incredibly conservative assumptions and never causing interference. We have no idea if we're 1 dB below the interference protection threshold or we're 60 dB. We don't know how many dBs we've left on the table because interference doesn't occur. If we had a feedback loop, CBRS actually does have a feedback loop. CBSDs, the base stations in CBRS, actually do, by FCC rule, have built into them the ability to report back to the spectrum access system the interference levels on different channels. Unfortunately, the manufacturers, although that is implemented technically on their CBSDs, they don't report any meaningful data back. They don't actually do an interference sweep. They report data, but it's all, -99. It's just some token number. But it's an example of, it would, like Needy said, be really useful if you could have a feedback loop so you know whether your propagation predictions, including clutter, are accurate or not, and whether the incumbent is getting interference.
Good. Thank you. So I'm going to switch the order in which I intended to ask these questions that I have, because there's one that I think could be addressed rather quickly, because the one that comes next might take a little more time. So this is the next question. What model configurations, outputs, and application program interfaces, APIs, are the most useful for your use of the clutter model? In other words, another use case, but we're talking about use cases of your organizations or your interested parties actually being the ones to try to integrate clutter into an existing model, use it, just a clutter model. What kinds of configurations? And what I mean by that is, would you like to run a clutter model completely independently? Do you already have a placeholder in the module and your propagation analysis things that will accommodate a color model? Chris, you want to start with that one?
Sure. I'll guess I'll come back to my question of, are we going to, we're assuming, well, a model like ITM, for example, is going to assume that effects are statistically independent. And what I mean by that is, there's a free space loss, there's a diffraction loss, and then if we talk about clutter, we're going to bolt that on, to the end as an additional loss term, right? So there's an assumption that these things happen independently, and you can all add them up at the end. And I've always asked the question, and again, it comes back to my question, is that the right assumption? Are these things statistically independent? Is there a difference between diffraction and adding clutter, and then a cluttered diffraction, if you will? That's a weird way of thinking about it, but it's clutter in the presence of diffraction. Should those two things be handled differently? And I think that's a bit of an open-ended, in my opinion, I think that's a bit of an open-ended question when you're talking about improving our understanding of cluttered models. So should we continue to treat things as independent elements of propagation, or should we start thinking about things as an integrated whole? And the reason that I bring that up, if you talk to somebody that's doing ray tracing propagation, right? Ray tracing is an integrated whole. And if you believe the folks that can do real-time ray tracing with, GPUs, they will say, give me 30 seconds and I can solve your entire domain and tell you all of what's going on. So
only if you have NVIDIA chips.
Only if you have NVIDIA chips, right. So I think, I think that what would be most valuable, for example, from an API perspective or a development perspective, is, can you parcel out those individual elements that the model is using, so that you could go through and ask some of these questions about should there be things that are integrated wholes rather than treated as independent blocks?
That's an interesting point, because TIREM and ITM are both what I call mode selectors, right? They go and do calculations for a number of modes because they're all happening at once, and they pick the one that wins, right? So that's a very interesting
But
point.
Chris,
Maybe they're not.
but in the end, whether you treat it as a whole or you take it as separates, in the whole, it has to work, and it has to be compared with measured data.
Mhm.
So I think rather than figuring out, the distinct pieces on how to solve the problem, how about incorporating measurement into it, right? And continuously calibrating and recalibrating your models based on actual measurements. And to Andy's point is, even though in CBRS there is a note in the report and order on measurement, but unless it's in the report and order and unless it's in the rules, it is not going to happen.
I can't laser point, but you're reading my point. My point exactly. Right there, the 1, 2, 3, fourth bullet point.
Fourth bullet point, and getting to the point
Supplement
is
with measurements. is what it
supplement
said.
with measurements, and that's what it requires. What I'm trying to say, it's a continuous process. It's not a one-time process. It's a continuous process, and there has to be some kind of an industry feedback on how to incorporate measurement data to that specific transmitter and receiver class, and do the modeling and so on.
That was my fifth bullet point.
Okay,
that you
well,
got.
I can't even see. You know what? The table is too high.
So, Andy, do you have a view of how Google or you would want to use
Yeah.
and incorporate?
It would have to be very fast. And the reason I say that is in the CBRS domain, which is the use case I'm here to represent, we have to deal with aggregate interference, which I think in the future, you need to find better ways to deal with aggregate interference than doing actual, series of propagation loss calculations and adding up all the resulting power. It takes a long time. We have about 380,000 CBSDs in the CBRS world, and the SAS administrators every night have to calculate aggregate interference from a large fraction of those devices into many points on a 2 arc-second grid in a 200 by 200 kilometer dynamic protection area times 50 different dynamic protection areas. And we have to do that for every pointing angle of the rotating radar beam that's on the ship in that dynamic protection area. And we have to do that for all 10 channels in the CBRS band every night. And it takes about 3 hours. You would think, Google has an infinite number of CPUs and all this other stuff. Turns out they still charge us to use them. So we have to try to optimize how much we do. But it takes about, and not just us, the other SAS administrators as well, it takes several hours to run these calculations every night. If we added a layer of clutter loss calculations to that, it needs to be fast. It can't greatly extend the time. And we would like in the CBRS world to get towards, to Chris's point, more real time. We'll never get to real time. I don't think we'll ever get to real time. I think Masood would agree. I don't think we'll ever get to real time interference calculations the way CBRS is set up right now. But even if we don't go to real time, whatever API or whatever way we do clutter loss calculations, it needs to be fast and efficient.
So, Easy, you want to take that one on, or did you already
I thought, yeah,
tied in with
I think
Chris?
as AT&T,
Yeah.
we rely a lot on measurement data.
Yeah.
I mean, and it can be done. What I'm trying to say, we are trying to solve a coexistence problem with some locations where you have federal assignments and federal assets, but we do it on a nationwide basis. We do it for different bands, nationwide, indoor, outdoor, different clutter classes, different morphology. So it can be solved. And the way and again, to going back to Andy's point, do you need to solve it for every dB or do you need to solve it for a 10 dB? And I think you really need to solve it for a 10 dB because beyond a certain distance, let's not make the problem a 100-mile problem, but make it a 10-mile problem. And then you can always solve it through mitigation, through coordination, through measurements, right? And that's how the problem gets solved. But and even in aggregation, at least in the ambit model, that at least what we are trying to do is we are sharing our network data. So our network, our base station, it measures aggregation from frequency reuse from all the other 5G base stations. And yes, it's not the aggregation at the radar location, but it can be an aggregation at a site which is the closest to the radar location at a height which is comparable. And that aggregation delta can be looked at and compared against the models. If it's a 6 dB aggregation compared to a 20 dB aggregation where the model is calculating, then you know there is a difference in the calculations and there's in the assumption set and so on. So again, I go back to the point on measurements, using the real network data and calibrating whether it's aggregation or whether it's calibrating your clutter models.
So on this point, can I ask the two of you a question that a friend of mine asked me about 20 years ago?
Wait a minute, who's the moderator here?
Do you care about correlation or causality?
One-word answers.
Do you care about
In
correlation?
your model, do you care about correlation? In other words, do you care that the model predicts X, Y, or Z, and you don't care why it gets that prediction? Or do you want to be able to trace back to the original physics what's causing something to happen?
I care about the causality because I can mitigate it then.
The correlation, you mean, or
Yeah.
the
I mean, I need to figure out what is causing the interference, and so that I can go and mitigate it.
I also think you're effectively asking whether AI is okay. If we don't really care to know what's causing the interference, we just need to be able to understand whether it's going to occur. I think for the sake of protecting the incumbents, that's all we care about. I think initially, maybe over longer timescales, we care about causality so we can make some adjustments and stuff. But I think on a night by night basis, when we do the interference calculations, I think we're okay just making sure the incumbent isn't going to be interfered with. We don't necessarily have to know exactly why they're not going to be interfered with.
And that's the difference in view when you're working with a licensee. We can go back and mitigate it. We know if we know exactly, like for example, you said it is one transmitter which is X distance away that's causing the problem, and I would mitigate that problem than rather having a ripple down effect where I have to close down 20 or hundreds of transmitters in that direction. And luckily for 5G and 6G, we have the tools to mitigate it. That there are a lot of tools available to mitigate it.
So I have one other question about statistics that I had prepared. However, we talked about statistics, the importance of it. We've studied your graphs, and
Yep.
those are as statistical as it gets, I guess. So could we maybe use the last 10 minutes for the audience questions? I think we have 10 minutes remaining. Do we?
About 10 minutes.
Yeah.
So thank you. Thanks, Andy, for portraying the misery of our life so cleverly. By the way, I'm from Federated
And
Wireless.
Masood's the world expert on CBRS. So if
Yes. So, but I want to. So even though the like a real-time operation, as Andy mentioned, creates a lot of problems, but I want to look at the other side, and from two angles, it might be useful using clutter. So number one is that I mean, if you look at the current discussion on DPA relaxations that hopefully next week we are going to announce, that has caused the area over which we apply the aggregate interference calculation significantly shrunk. So for example, today, if you look at one of the DPAs, the dynamic protection area, we call it East 1 in Norfolk, the distance that we need to take into account the CBSTs is about 368 kilometer. So any CBST which is located up to 368 kilometer from the shore, we need to take into account into calculating aggregate interference. With the changes that are upcoming, and hopefully next week we are going to announce, that's 368 has been shrunk to 80 kilometer, which means that the number of transmitters that we take into account are significantly less. And the reason that has happened is because of some of the relaxations, including the clutter that has been introduced. Oh. So when clutter is introduced and we are able to take into account some of the real factors and not to be very conservative, that can, even though everything Andy said is correct in terms of the complexity, but because the number of transmitters are going to go down, hopefully that would be helpful. So that's one thing that I really don't want to kind of leave aside the real-time clutter because of the complexity for the reason that I mentioned. And the second thing I want to mention is that it's really important how we are going to take into account the clutter. Because I just had a discussion with Billy over lunch that, for example, if there are a way that instead of asking like the DSS or like SAS or any type of spectrum sharing, central spectrum sharing system to do the real-time calculation of clutter, but rather those informations can be provided as a database, the same way that, for example, terrain heights are provided to us today, the databases for ITM. If those informations can be provided, then that would significantly reduce the amount of real-time calculation that we need to do for clutter contribution. So there are ways that to handle that, but things about the complexity that Andy said is correct. Sorry, it was lengthy.
Well,
Go ahead.
I was going to say, could I say, be careful what you ask for? A clutter map, if you will, right? One of the things that I've seen when people have done some basic exploration of this idea is that it becomes very dependent on the geometry. So in other words, if you are propagating through a building in one direction versus another direction, you can see vastly different attenuation levels. And so you may reduce your complexity on one side, but significantly increase it in another way.
We need to think about that. It's not just a simple problem.
Right.
Do we have another question out there? Yes, no?
Searching the room. I don't see a hand. And online as well. Feel free to put a question in the chat. A few more minutes.
So this question is regarding Andy's slide that you showed earlier. So as far as I understand, I think you mentioned that these measurements were taken at a distance of about 10 kilometers?
Over an area of about 10 kilometers.
10 kilometers.
Yeah.
And in the first case, you have your transmitter up at 63 meters.
We had an apartment building and we put it down the same stack of apartments at different heights. So we had, I think, 5 different heights. I
Okay,
was just showing this 2 extremes.
I see. Okay.
Yeah.
And I noticed that the horizon distance is, because you're about 30 meters above clutter height, the
Yeah.
horizon distance is like 20 kilometers plus.
Quite far. Yes.
So basically what you're measuring should be just free space path loss, isn't it?
So no, because there are tall buildings around this building now. That at the time, and one of the points I wanted to make is that clutter, even in a city, changes very quickly. Buildings come down, buildings go up. But anyway, but at the time, there were buildings in various directions, several blocks away, that were a little higher than ours. So we didn't have free space, but we did have free space in certain directions. And in fact, I didn't get into it, but we drove about 60 miles away to, they call it a mountain, on the East Coast. It's not really a mountain, but a mountain about 60 miles to the west of DC. And suddenly we could pick our signal up again. And that actually agreed quite well with ITM because there was no clutter. That's why we could see it. But yeah, so there was still clutter even at that higher, but we were above most of the clutter at that point.
Yeah, my question is relating to how you could be measuring less than the Longley rise when all you're really experiencing is either clutter or free space path loss, but no diffraction and nothing, no troposcatter or anything like that.
So how can it be less than free
Yes.
space? Okay, so actually remember, ITM is a statistical model, right? So even at 50%, if you just put in, if you've got a free space situation, it will calculate for 50% of the time you're going to be below that predicted amount, and 50% of the time you're going to be above that predicted amount. Free space loss is not necessarily just a static value, especially in an environment where you may not have clutter on your path, but to Chris's point, the world is 3-dimensional. That vertical path may be free space line of sight, but you've got signals that could be contributing, that could be bouncing off of other buildings and airplanes and all sorts of other stuff that is also contributing to the signal strength. And that's why you don't get free space loss and only free space loss. You can get more, you can get less. It just depends on what's happening on these alternative ray paths.
It's constructive wavefront interference, like when you bounce a wave off the pavement as well as a direct ray. If they add in phase, guess what? You get 6 dB more power at that point in space.
Yep.
Yes. And in urban canyons, you can get even more. And shall I say, more clutter gain?
Yeah. And it doesn't have to. And it doesn't have to be in
It's
phase.
not a gain. It's not a gain.
Yeah, it doesn't even have to be in phase, because if you're adding power over a certain bandwidth, and we're using a CW signal for the propagation measurement, they can be two different Doppler shifts, and so they don't end up. It's not a constructive or destructive interference issue anymore. It's just two different CW signals showing up in the same bandpass, and they just add together.
So if there's, did you have another question back there?
We've got one more if you want to take it.
I want to give Chris at least 2 minutes to show his last slide, right?
Yeah.
Oh, you wanted to
save
see
it
the
for some-
bonus? The only thing that I was going to point out here, this was a slide shared with at the last minute by a friend of mine, and this gets to the point that the world is 3 dimensions, and it gets to this point that I was making with Masood about be careful what you ask for when you say a clutter map, and it's this is an example of a cellular system where things are pointed down, right? You're trying to serve customers that are at street level. And yet the geometry is such that as the signals reflect off of a building, they will actually cause interference to a victim satellite receiver that's actually operating up in space. And it gets to this point of the world is 3 dimensions. How do we model the world in 3 dimensions? But moreover, how do we model clutter in 3 dimensions, right? Because it's not just about adding necessarily an attenuation term. In this case, the clutter is actually causing an enhancement over what the model might predict, because the model would predict a side lobe to side lobe interaction here, and yet, like is shown in the diagram here, you can get a reflection or off of a rooftop. You can get a reflection off of a rooftop that will land in a position that could potentially cause interference to a receiver.
Is this a reported case, or is this just
Both, yes.
It is reported.
Yes.
Hence clutter gain.
Oh.
Can we have one more question
can.
from the audience?
We cannot let you off the hook yet.
Oh,
So let's see this last question.
be kind.
We'll go back to that first slide again. So for Lonely Rice, it generates error codes, error 3s, error 4s. If you're within a kilometer, you'll get an error 4 code out every time.
Yeah.
So have you run this and produced that map with those isolated, taken out of the calculation?
We did. So we log all of the error codes that come out of ITM, because you can get error codes for other reasons other than being closer than a kilometer. Most of our measurements were beyond a kilometer, and so they weren't included. But the data I showed probably still had some residual error codes in it. This is from 4 years ago. We ran some passes where we took out anything that reported an error code. Didn't make a tremendous difference, fraction of a dB or something like that.
It's a big question on error 3 codes, because you get the dual diffraction, and those you have a lot of issues, horizon issues, especially when you start doing clutter modeling in those cases. So I was curious if those were excluded as well in that plot, or if those were also included
In
the error
those
3
plots,
codes.
no, but years ago when we were doing this, we did rerun all of the analyses, excluding all the error codes.
And your means were lining up pretty much between with and without?
Yes, fraction of a dB difference in the means. And it was because the ones with error codes were a very small percentage of the total number. We had like 2 million total collected points. And so the number of reported error codes was a very small fraction of that 2 million points.
All right, thank you.
So one thing to point out there real quick is on the right-hand side, that second bullet point about preconditions on transmitter receiver.
Yeah.
So ITM and EHATA, which is the other model that's talked about in CBRS world, the models themselves, when you dig into them, have some preconditions on the transmitter sighting. In other words, how it assumes the transmitter's being installed. You put yours, in a hotel room in a building. Is that
Put
right?
on balconies of an apartment building.
So that may not actually meet the
Right.
precondition.
And guess what? Unfortunately, the CBRS standards and the rules don't say you only use ITM if you meet the preconditions. They say you use ITM.
Yeah.
So yes, you're right. I'm not going to say you're probably, there's a 95% probability you're right, but the way it's implemented is that's just the way the standards
So we
work.
covered statistics.
Yeah.
too.
So we covered statistics.
Yeah. 6 gigahertz is better. They did take into it. Yep.
There are some
Yep. Yep.
preconditions.
So
Yep.
we've reached the witching hour for this particular panel. I want to really thank these folks. They did, I thought, a really good job, considering the fact that less than a week ago, 2 of the original panelists dropped out. Chris came
Yes,
in
thank you,
all
Chris.
dressed up,
Yes, you're welcome.
overdressed.
Yes.
So thank you.
So you have a separate bio leaf, I understand.
Yes, you get your own bio.
You
I get my own bio, yeah.
The highlight.
Kelly, for moderating. Thank you, panel.
All right.